One of the most powerful applications of calculus is what is called optimization. So in certain situations, you want to operate as efficiently as possible. So for instance, if you're a corporation, you want to maximize your profit. If you're building something, you would like to minimize the cost of doing so. And in most cases, there's a function that represents either the profit or the cost, and there's an interval on which the variables make physical sense, and we're trying to maximize or minimize that function on that interval. So let's take a look at a graph here. So here we have an interval. A, B is the interval, and our function is f of x. And we're looking for the absolute biggest value if we're trying to maximize things, and we're looking for the absolute smallest value if we're trying to minimize things. And what we can see is the left-hand endpoint has the smallest value on the interval, which we will call the global minimum. And this top of a hill here has the largest function value, which we will call the global maximum. So some definitions. F of x has a global maximum at c on the interval I if f of c is bigger than or equal to f of x for every x on I. So the idea here is the biggest function value occurs at c, everything else is less than or equal to it, and f of x has a global minimum at c if the function value there is less than or equal to every other function value on the interval I. Now, some terminology. The plural of maximum is maxima, and the plural of minimum is minima, and that's why this title is Global Maxima and Minima, because we're talking about several. Now, let's have a look at the locations of the global maxima and minima. The global minimum is at an endpoint. So one of the things we're going to have to worry about is an endpoint. The global maximum is at the top of a hill, and you can see here that this hill has a horizontal tangent. So one of the things we're going to be looking at are places where the tangent is horizontal, which means the derivative is 0. However, not every top of hill or bottom of valley has a horizontal tangent. If we look here, we can see that our global max actually happens at a corner. So it's also possible that the derivative won't exist there. Thus, we define the following. A critical number c is a real number in the domain of f of x such that either f prime of c is 0 or f prime of c does not exist. If c is a critical number, we call c, f of c, a critical point. So a critical number is in the domain. You have to be able to evaluate the function there. And the derivative there is either going to be 0 or it does not exist. Now, let's take a look at the theorem that's going to let us do everything. Let f of x be continuous on the closed interval ab, which is sort of the pictures we've got. Then f of x has both a global maximum value and the global minimum value on that interval. Those values occur either at critical points or at endpoints of the interval. So if we've got a continuous function closed interval, we know that we're going to have a global maximum and a global minimum, and this theorem tells us where to look for them. So some more alternate language. Sometimes we refer to global maxima and minima as absolute maxima and minima. So the global maximum and the absolute maximum are exactly the same thing. Now, another thing to notice. There's one maximum value, but it might happen at multiple places. So let's take a look at y equals sine x. We know the maximum value of sine x is 1, but if we look at this graph, it happens here and here. The minimum value is -1 for sine x, and we see it happens here and here. So we might have multiple locations for the global maximum and multiple locations for the global minimum. Let's take a little more careful look at the theorem, which says f of x is continuous on the closed interval AB. Then f of x has both a global maximum value and a global minimum value, and it tells us where to find them. Now, what's important is f of x must be continuous and the interval must be closed, or the maximum and or the minimum may not exist. Okay, so if we're going to use this theorem, these two things have to be true. Now, it may turn out, even if they're not true, there is a maximum and a minimum, it's just not guaranteed. So let's take a look and see why we need these things. So here's the graph of a function, and it's on the open interval 0, 1. So 0 and 1 are not included. And as you can see here, the maximum value ought to be 1 because that's where all of the function values are headed, except 1 is not one of the function values. So there's no maximum here. And if you look this direction, the function values are headed to 0, except 0 is not a function value. So there's no minimum here either. So open interval, we could be in trouble. Here's another situation, closed interval between 0 and 2, but this time we've got a discontinuity. Same sort of situation as we had up here, the function's values head to 1, but you never see a function value of 1. Here the function values heads toward -1, but you never see a function value of -1. This function doesn't have a global maximum or a global minimum on this interval. Now let's use what we've just talked about to find the global maximum and global minimum values of a function f of x on a closed interval. So here's f of x, it's x cubed minus 6x squared plus 3. Our closed interval is -2 to 2. Our theorem says that if f of x is continuous on a closed interval, and notice that this is a polynomial, so it is continuous, the interval is closed, the global maximum or minimum for the function on that interval occurs either at a critical point or at an end point. Okay, so the first step is to find critical points, and what we'll be hunting for are the x coordinates of the critical points, which are called critical numbers. So we take the derivative, and the derivative of x cubed is 3x squared, the derivative of minus 6x squared is minus 12x. And we can factor a 3x out, and we get 3x times x minus 4. Now we're looking for places where that derivative is 0, which is going to give us the critical numbers. So 3x times x minus 4 equals 0, and we get x equals 0 or x equals 4. However, 4 is not on the interval -2 to 2. So the only critical number we consider is x equals 0, which is on that interval. We also have to include the interval endpoints in the x values that we're going to check, and the endpoints are x equals -2 and x equals 2. So including 0 into that list, we have 3 values that we need to test. Now the way we're going to test them is we're going to put those values into the function and see what function values come out. So when x is 0, 0, 0, 3, you get a 3. When we evaluate the function at -2, we get -2 cubed minus 6 times -2 squared plus 3, which is -29. And when we evaluate the function at 2, we get 2 cubed minus 6 times 2 squared plus 3, which works out to be -13. Now we want to find the global maximum and global minimum values of the function. Those appear in this column. The biggest value is 3, which is the global maximum value. And the smallest value is -29, which is the global minimum value. So on the closed interval -2 to 2, the global maximum value of 3 for the function occurs when x equals 0, and the global minimum value of -29 occurs when x equals -2. So Maximum function value of 3 occurs when x equals 0. Minimum function value of minus 29 occurs when x equals minus 2. Closely connected to the theory of global maxima and minima is that of local maxima and local minima. Now, a global maximum is the biggest function value anywhere in your interval. A local maximum is the biggest function value in the vicinity. So for instance, right here, this is a local maximum, looks like the top of a hill. This is a local minimum, looks like the bottom of a valley. Here's another local maximum. In general, we do not consider endpoints as local maxima or minima, even though this is the smallest in the area. In some sense, it's not in the vicinity. The neighborhood doesn't extend past the point. Same idea here. So when we talk about local maxima and local minima, we will not be talking about endpoints. Now, if you look at this, that local maximum is also the global maximum. So it is possible for a local maximum or a local minimum also to be the global minimum. However, not every local maximum or minimum is global, as you can see here. Local maxima and local minima occur at critical points. Top of hill, bottom of valley, top of hill. Those are all critical points. Here in this picture, the tangents are horizontal, but if we drew the other picture that we saw previously where there was a corner at our maximum, you could see that the derivative might not exist there. However, local maxima and local minima always occur at critical points. So when we hunted for global maxima and global minima by looking for critical points, we were also finding locations where there might be local maxima and local minima. Now, an important point, although every local maximum or local minimum occurs at a critical point, not every critical point is a local maximum or a local minimum. And if you look here at the graph y equals x cubed, here's an example. That's a horizontal tangent, so that is a critical point. However, we go up in this direction, so this can't be a maximum. We go down in this direction, that can't be a minimum. So as I said, although every local maximum or minimum occurs at a critical point, not every critical point is a local maximum or a local minimum.